Hello, this is Brian Kirch with Altera Corporation. Just wanted to do a little bit of under-the-radar evangelizing here of a nifty little new tool that we have. It's a Simulink-based tool. It's actually an add-on kind of next generation of DSP Builder. And before I kind of get started into it, I would like to talk a little bit about kind of what the tool, what we envision it being used for, and its strengths and weaknesses. I think in the past there's been a lot of people who have looked at the existing Simulink-based design methodologies in the past and have formed pretty quick and a lot of times justified opinions about where it's useful and how its productivity rates against that of traditional HDL. And I think this is actually a tool that can really rebalance that equation quite a bit. In the past, I think the strength of DSP Builder flows have been for things that are feed-forward in nature. It's been the big advantage for places where you want to have an integrated test bench with MATLAB. But some of the challenges have been state machines surrounding control issues. It's been around parameterization, pipelining a design, and these are things that really Advanced DSP Builder was really targeted to create and enhance for us. So if we take a look at that from that perspective, I think that you'll still see that the target markets that make sense will be things like remote radio heads, so doing up conversion, down conversion, crest factor reduction. In some places in the video world, I could see SAT engines as being something very effective, and certainly in the military space, where you're doing things like beamforming or radar applications. So really anything that's feed-forward in nature is going to be a really good target, or places that you want to create portable IP that can run across a different number of channels if it needs different target devices, a low power, a high power version. All that stuff is going to be enabled with this flow. So what I want to do actually is just jump into a very simple design I think that illustrates what is unique about this and perhaps why it might be advantageous for not only a prior DSP Builder user but even for the hardest of hardcore VHDL gurus. So this is a simple fur filter that I put together. DSP Builder Advanced is really just a bunch of blocks that are added on top of regular Simulink blocks. In the past, we've also had the older and still supported DSP Builder block set, and these block sets had lower level blocks like multipliers and adders, dividers, everything that you had in Simulink. The difference is that they had hardware attributes associated to them, so things like pipelining, clock enables, all of those sorts of things. If you go look at the Advanced DSP Builder blocks, you really see that there's not any of these. There's the same math blocks, but they don't really have any parameterization associated with their pipelining. So if we take a look at this design, again we've got a block to open up Chorus. I've already done that to speed that process up. A little bit of information about how fast we want the chip to run and some control things that actually generates the HDL. So I'm going to take a look at this design. It's relatively simple. It's just a valid, a channel, and some data, and it comes out with a valid, some channel, and some data. So a pretty standard streaming type architecture. So if I drive in here, I'm specifying a device, in this case our newest Stratix 4 40 nanometer device. And what I'm going to do, and for the sake of doing this live, is I'm going to go ahead and start a simulation. And what that's actually going to do is generate HDL. So you can see it's already done that. And in the background while I'm talking, I'm just going to go and kick off Chorus so that you can see this. So here's the top level of the particular design that we have. And as you can kind of tell looking at it, it's a simple 8-tap fur filter. And if you look at it, it's pretty much like exactly what you'd expect to see out of a textbook. You've got some tap delay lines here. And then you've got some multipliers that are multiplying against some set of coefficients. And then finally an adder tree, which propagates all the way through. And if you look at this, you can see there's a couple things that are a little bit different than what you would normally expect for a tool that is doing a FPGA design. Essentially, you only have pipelining for the tap delay lines themselves. And that's because that's the natural delay that you actually need for the algorithm to work. But the multipliers and the adders themselves have no delay. In fact, if I were to run the simulation, I would see that the data that's at this point actually propagates all the way through into the output in a single clock cycle. So from the purpose of designing and developing my algorithm in the Simulink environment, it vastly simplifies it for us. You can see that we also take advantage of the Simulink facilities for bit growth and all of those sorts of things that are available. So you kind of may be asking, well, how are we actually doing this? What's actually occurring? Well, at the beginning here, we actually have a simple structure where we have a valid, a channel, and then some number of data samples. Now in this case, we only have a single data sample, but there could be an arbitrary number depending on the algorithm that you're working. So we really rely on the fact that the data comes in aligned with this time block, and the data goes out aligned with this time block. This is a channel in and a channel out block. We really otherwise don't care what happens in between, when we really, in a lot of cases, don't care how long it takes, so long as we get the right results on the output. So what the tool does is we give it a timing requirement, an Fmax requirement, and Advanced DSP Builder has all the information it needs to understand how to get a design to run at a particular speed on the FPGA. So it knows how fast the carry chains are, how fast the LUTs are, how fast the multipliers and memories are, and pipelines accordingly. In addition to that, it balances all the pipelines. So in this case, it's a relatively straightforward process about how you would pipeline the design going forward. And in a later section, we'll actually show you how that process even works for feedback loops. So for accumulators coming back around, or IIR filters in the example that we'll show later. So this is a very nice way of doing your design because it takes a lot of the control information out of it. What it also does is it means that when you do your IP design, it's not device specific. And what I mean by that is that when you go and you target a Stratix device or a Cyclone device and you pipeline it to run at a certain speed, you actually are putting in the control structure so it runs at that rate. In this way, you can go and take and do one design that targets to a Cyclone or targets to a Stratix device, both at the same rate. The difference being is that the Stratix device will take fewer resources. So this is a very nifty little thing. You can see that there's a couple things that I wanted to point out here on the output. It is important in a lot of cases to know what your latency is in case you want to match with something else. And in this case, the tool tells you how much latency it added. And here it was 10 clocks. And what it will do is it'll actually put all the latency in this block itself. So internal to design, I see no latency. But on the output, or at the top level of the design, I will see all the latency that is added into this design in my simulation so that I can correctly model and simulate it in part of a larger design. Now, if I go up to the top again, there's some nice little context-sensitive help that we have, and if I go to help here, we can go take a look at the bottom, and we're going to skip through this. This is actually a memory map for my coefficients, but it also gives me some resource usage here at the bottom. In this case, it's saying 1,000 LUTs and 8 multipliers. And this is actually data that it receives when you run the simulation. It actually generates the RTL at the moment that you run the simulation. It only takes a few seconds. And because it's generating pipeline code, it actually knows exactly what the resources should be, and it tends to be very accurate pending the optimizations that Quartus does. So if we go take a look at this, you can see that this is the report of the design. We went ahead and ran it. I was going to do it live, but it pulls down the processor enough that some of the audio starts to cut out. And so you can see from the fitter here that it took about 912 registers, which is within 10% of what Advanced DSP Builder reported, and then 8 multipliers, so 8 18 by 18 blocks. And if we go look at the Fmax, back over here, we had requested 400 megahertz, and the bus, which we'll talk about later, to run at 200 megahertz. And you can see that indeed we got 451 megahertz push button for Stratix 4. And 327 megahertz for the bus clock, which is our processor interface. So that just kind of gives us a very brief background of what Advanced DSP Builder is capable of in terms of a very pure sense. And the next two sections, we're going to look at how does this work for different types of designs, designs that might have some feedback. So kind of give it just another little perspective, and then we'll go look at some of the IP functions that are included. I'd also like to point out that there's a couple additional things and directions that we're taking this tool for further releases that are, I believe, as innovative or more innovative than what we've shown here. So if this does have any interest to you, be sure to contact